Chapter 3, Atomic Structure in the Periodic Table. I wonder why they put those two in the same chapter. Have you read ahead? Chapter 3? No. You don't want to spoil the ending? Atomic structure and the periodic table are in the same chapter because the way the periodic table is organized, you can deduce much of atomic structure for each of the elements from the table. And we'll eventually get there. All right. So a little history. I got this from somebody, I don't remember the guy's name, puts these things together called compound interest. Just little charts that summarize various things. They're not all chemistry. Some of them are physics and some of them are biology. But if we go back to the structure of the atom and we look at what the prevailing theories were at the time, John Dalton's idea, and everybody believed at that time, sign in before you sit down. They just, right over here, they just thought the atom was a jelly-filled sack. Kind of like cells. They thought the same thing about cells. Then came, well, now, I don't want to, yeah, maybe I better. So, John Dalton introduced the concept of the atom. Well, actually, he brought it forward from the Greeks. The ancient Greeks thought, some of them thought that everything was made of an elementary particle they call the atom. Right? Did I talk about this last time? I didn't, did I? Okay. The Greeks called it an atom because this part of the word, tomos, is to cut or to divide. And whenever you put an A in front of something, it means not. So they said, you can't divide it any further. The atom is the smallest particle that retains the properties, well, we sort of added this later, that retains the properties of the substance. Well, the Greeks, the ones who believed in were atomists, thought that everything was made of the same atom. That's a problem, right? Because how do you get all these different elements from the same atom? So they had to introduce other ideas to their atomist theories in order to get the atoms to behave the way they wanted them to for different elements. Well, Dalton brought that forward, but he changed one thing. He said the atom of this element is the elementary particle of that element, but the atom of another element is different than that atom. So that's where John Dalton brought us. And he was right. Each element has a different atom. Then we start looking, we find out when about a century later, J.J. Thomson proved the existence of a subatomic particle which had a negative charge that came from atoms. He used the cathode ray tube to prove it. And he called it the electron. So now we've got an elementary particle. We know that the atom now is not just a jelly-filled sack. We know it's still neutral. So J.J. Thomson comes along with his negative particle. So we have to have positive balance to it. By this time, we knew that negatives and positives attract one another. And when you have the same number of negative particles, or actually the same charge, negative as positive, they cancel or they neutralize. So we knew that there had to be an equal amount of positive charge in the atom. Well, Thomson's idea at that time was what we came to call the plum pudding model. You ever seen a plum pudding or eaten plum pudding? It's not bad, but it's a pudding with bits of plum scattered throughout. So if you say the atom is a plum pudding, then you got these negative particles scattered throughout this positive jelly that neutralizes it. So that was the plum pudding model. Well, it didn't take long before an English scientist named Ernest Rutherford said, this makes no sense. I'm not sure what his reasoning was, but he proposed a different model for the atom called the nuclear model. And what he said was, the negative particles are there, definitely, but there's also a particle of equal charge to each one of the negative charges, but it's massively larger than the negative because they knew something about the weight of each atom at that time. And they knew that well, let me back up. J.J. Thomson also determined in his experiments the charge to mass ratio of the electron. He couldn't define what the mass of the electron was, but they were pretty sure it was really small. So Rutherford said, in order to balance the charges, you need other positive charged particles, subatomic particles, to balance the charge, but they have to be massive in order to make up for the mass of each atom. So he proposed the nuclear model, and Rutherford said that the atom is made up of a densely packed nucleus with these positive particles in it. Let's see, which one is that? Beryllium? Yeah, that's beryllium. And then the negative, the electrons were out here. Most of the mass is in the nucleus. So whenever you propose a theory like that, or a model, you better have a way to prove it. So Rutherford devised this experiment. At this time, at the beginning of the 20th century, it's not included there, but a Frenchman, Henri Becquerel, had shown that there are three basic forms of radioactivity that were coming from not decomposing. I forget the right term. Well, let me go to what the particles were. He said there are three, and he gave them Greek letters. He said the gamma radiation is high energy light. It has no mass. Of course, we know that's not right, but anyway, this is light. Very high energy, right? You've heard of gamma ray bursts in the news, right? They're coming from way, 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 way far away, thank goodness. And they're very directional, but they're extremely powerful. If the Earth got caught in line with the gamma ray burst, it could potentially just rip our atmosphere completely off, which would be bad. So gamma ray is the highest energy light that we know of. And then he said there was another particle, the beta particle. This is essentially a very fast-moving electron, high-energy electron, coming from the nucleus. And the last one he proposed was alpha particle. And this is essentially a helium nucleus with a 2+ charge. It has no electrons. It's just the nucleus of the helium atom. But it's coming from the nucleus of a radioactive substance. So I said that to say Ernest Rutherford was also working with, a lot of scientists were working with these radioactive nuclides. And what he wanted was a very heavy particle that he could fire at a thin film of atoms. And the thin film he chose was gold. Because in those, it had been known for centuries how to make really, really, really thin sheets of gold, like just paper thin, just a few atoms thick. Right? The Capitol down in Charleston was covered with just a few ounces of gold. It didn't take much. But he used this really thin sheet of gold. He needed just a few atoms thick because if he fired these alpha particles at the gold and there were too many atoms in the layer, it would just stop them all. His experiment would be done, would be over. So he got this thin sheet of gold and he fired these electrons at it, these alpha particles at it. And he had detectors set up all around. So here we have our big box of lead. All right, what's the symbol for lead? Remember? Pb. That's shielding, right? So this radionuclide is in here. I don't remember which one it was, but probably radium. But the alpha particles were taking off, and they were going every which way, whatever direction. So he needed a straight beam. So he used what's called a collimator. It's simply just two slits aligned like this. And only the ones, you could get some coming through like this and like that, but only the ones that went straight through would get through both of them. And so now he has a straight beam of alpha particles. And he fires them at the gold foil. Symbol for gold. Eight what? Close. That's silver. Yes, AU. Okay. So now he fires these alpha particles at that gold foil, and he's got detectors all around. So when they strike the foil, most of them go straight on through. Make a dot there. He probably used film in those days. So that means that either the plum pudding model is accurate or most of the space in an atom is empty. But he also saw a deflection of these particles. Some of them went this way, some of them that way. And this is largely due to the positive charge on the nucleus and the attraction of the electrons in the outer regions deflected them. But some of them came straight back. Those are the ones that actually struck the nucleus. So he knew then that his theory was right. So Ernest Rutherford had proved the nuclear model for the atom, and the plum pudding model was dead. All right. Rutherford also had a research assistant, a graduate student, who later became his research assistant. His name was Chadwick. That's not on the slide here. Because they knew that with a nuclear model that has protons in it, only satisfied the mass equation for an atom for hydrogen. Anything bigger, you don't have enough mass in those protons to give you the total mass of the atom, right? So there must be something else in there, about as heavy as the proton, but with no charge, because it already balanced the charges with the protons. So he sent Chadwick on his detective mission to find out what that was, and he found out it was a neutron. So he proved the existence of the neutron. And we usually write it like this with a zero up there. It means it's no charge. So now we have the three elementary particles of any atom are the protons, neutrons, and electrons. Let's see. Oh, by the way, Rutherford got a Nobel Prize for his work. And then Chadwick got a Nobel Prize for his work. Another person that's not on here is Millikan, Robert Millikan. He was an American, and he took, I can't remember the year. He took the problem of J.J. Thomson's electron, which they didn't know the mass of it, but he devised an experiment where he could determine what the elementary charge of an electron was. And he had this vacuum chamber set up, and he had a little window in the side, and he had a telescope in there so he could watch. He could watch these oil drops. Right? So he had oil that was sprayed into very fine drops, and then he had two plates. Right? So he had this positive plate and had this negative plate. And the charge on the plates was calibrated so that he could tell what is the charge on each oil drop that he watches. They would fall under gravity through a little hole here, and he could watch them. He has a scale on the other side. And he could watch them falling with gravity. He did a calculation with that one. And then he changed the charge, the electric field on his plates, so that the drop would stop. And he knew from the electric field strength what the charge on each one of those drops was. And he and his students did this experiment thousands of times. And he got this huge amount of data. And the short story is he determined the elementary charge on an electron. So now that he knows the elementary charge, he goes back to Thomson's charge mass ratio, calculates the mass of the electron. It was very, very close. It's since been refined further, but he, for that work and some other work that he did to confirm experimentally the photoelectric effect that Einstein got he got a Nobel Prize for his, then Millikan came along and proved Einstein's theory with practical experiments, and he got a Nobel for that one. That's back when Nobel Prizes actually meant something. Okay. So I'm wondering if I need to go on here. There are some, when we talk about the structure of the atom, we need more information. And there was as usual, in true science, there was controversy after controversy about what was the structure of the atom. And we get major players in there. One of those was Niels Bohr, and the other one was Erwin Schrödinger. And I think what I'm going to do is leave that discussion till later when we get more information under our belts. Okay, so now we've got the subatomic particles. The electron is outside the nucleus with a negative charge. Protons and neutrons are inside the nucleus, very densely packed. The protons carry the positive charge, the neutrons have no charge. Now, is anybody wondering how you get protons, positive charges so close together? Nobody cares? They're packed really close in that nucleus. Now, with hydrogen, it doesn't matter. It's only got one. But once you start getting up there with two for helium, then you get two neutrons also. And then you get three for lithium, and you get three neutrons also. And as the atoms get bigger and bigger and bigger, you need more and more neutrons, not just equal to the number of protons, but much, much, much greater. And to make a long story short, there are four fundamental forces in the universe. Right? The weakest one is gravity. The other one is electrostatic. Or actually, they combine that into electromagnetic. Then there's the weak nuclear force and the strong nuclear force. The weak nuclear force is responsible for decay. That's the word I was looking for. radioactive decay. And the strong nuclear force is what holds the nucleus together. And there are various theories about it. I won't bore you with those. But one of the things that you need to hold the nucleus together is the neutrons. It's believed that they're exchanging some subatomic particle that allows all these positive charges to remain together. All right. So here we have a comparison of charges and masses. Notice that the electron is about, well, let's see, that would be 9.1 times 10 to the minus 28 is almost 10 to the minus 27, isn't it? Pretty close. So we're about 3 orders of magnitude, 3.5 orders of magnitude difference between the proton and the electron. I think the number, well, there it is, 1,837 times heavier. The neutron is just a little bit heavier than the proton. And what we've come to realize is that when the neutron, when there's a decay event, an electron can come from the neutron. That's where the beta particle comes from. And when that happens, the neutron becomes a proton, plus some energy. Okay, does everybody have a copy of these? Yeah, I see copies. Okay, good. I thought I handed them out last week. Okay, so this is just rehashes what I've told you already. Nucleus, small, dense, positively charged center of an atom. Has protons and neutrons in it. Now the whole atom, if it's not given a charge, remember, I know I showed you this one. Right. 4 positions around there reserved for information. Did I show you that one? No? Okay, I'll show you now then. This position around the element symbol is reserved for the charge. This one is reserved for the number of atoms. This position is reserved, and it's designated Z, is the atomic number. That's the number of protons. Okay. This symbol and the number of protons are joined at the hip. If you know one, you know the other. The element is determined by the number of protons. Right? So if I say 17 protons are in that nucleus, and you can look up the periodic table and find that's chlorine. Okay, that's the atomic number. This number, the mass number, is the number of protons plus the number of neutrons. And that one can vary. As long as you have the fixed number of protons, then this one can vary with different numbers of neutrons. That's called an isotope. So if you know this one and this one, you can find out how many neutrons, right? Just A minus Z is the number of neutrons. Okay. If there's no number here, or if we put a 0, of course, it's neutral. If you put a negative or a positive number here, that's a symbol for an ion. But if it's neutral, if there's no charge, then the number of protons equals the number of electrons. Okay, that's how you get a neutral atom. All right. I've already told you that. I stole my own thunder. And there's the animation for for the symbol. Symbol's got an A and a Z and a charge maybe, and then a number of atoms. So if I write, I had you memorize which ones are diatomic at room temperature and 1 atmosphere pressure. And those were the diatomic, they're all gases. Not all of them, excuse me. Hydrogen, nitrogen, oxygen, fluorine, and chlorine are all gases, and they're diatomic. So if I write this, that means there are 2 chlorine atoms bound together as a single unit. That's a molecule of chlorine. Or if I say bromine, and then I can also say this is a gas, but this is a liquid. And I can also say iodine. That's the way iodine is. It's a solid. Okay. Those are all diatomics. To illustrate that position where you have a number of atoms. But when you write a compound, that's where you also say how many of this atoms are in the compound. For instance, there you go, sodium with 11 protons. If you change the number of protons, you got a different element. So sodium has a mass number of 23, so how many neutrons does it have? 12, right? 12 plus 11 is 23. All right, elements are pure substances. That is, they cannot be, their identity cannot be reduced any further by physical or chemical means. You can't separate an element from itself. Yes, that's one way to put it. And every element is composed of similar atoms. I say similar because they're always isotopes, but they all have the same number of protons. Let's see. Yes, they all have the same atomic number. That's true. I didn't mention, how do we know they have this atomic number? Where'd the atomic number come from? Right? I just threw it out there that we had the protons and we knew the protons were represented for each element. But actually, the shoot, can't remember the guy's name now. I'll come back to it. And they all possess the same chemical properties, even if they have different neutrons. They have the same chemical properties. And they have the same chemical properties, well, ultimately because of the protons, but the electrons determine the chemical properties, right? Because we determine chemical properties based upon how they react with other elements. So when two atoms of the same or different elements approach one another, what do they see first? They see electrons. So electron interaction is where the chemistry happens. That's where we're going to place our focus, is going to be on electrons. And then we have isotopes. You can have every element in that periodic table is a composite of different isotopes. Most of them have a dominant single isotope, and then you have some minor isotopes. So when you look at the upper left-hand corner in that chart, you see that number is a weighted average of these values for those atoms. So if they're mostly one type, like carbon is mostly carbon 12, and there's some carbon 13 and a little bit of 14, maybe some 11, but most of it is carbon 12. So its atomic mass, not the mass number, but its atomic mass is 12.01. It's a weighted average. It's kind of like doing your GPA. This course is worth how many credits? 4? I think 4. Okay. If you get an A in this course, it carries a whole lot more weight than an A in a 2-hour course. That's the idea. There are some, I think one is chlorine, which has a mass number that's midway between 35 and 37, I think. So it's going to have, no, 36, excuse me, 36. So it's going to have one that's weighted about evenly between the two. But it still has 17 protons. Silicon, here's silicon example. It just runs through same number of protons, different number of neutrons. So those are isotopes. Now, if you look in a, let's see, some reference manual, CRC handbook comes to mind, and you look up the number of isotopes of each element. You go to that section of the handbook, and you see each element. It's got a list that long. Most of them, it's got a huge list. Most of them are very minor concentrations of the, and one is dominant. Some of them might even be radioactive. All right. So the mass number of this one is 51, 23 plus 28 neutrons. Okay. So what element is it? It has 23 protons, right? Just look up there on the table. The atomic numbers and the atomic weights get bigger from left to right and top to bottom. So you can just move along until you find the right one, right? 23, which one is that? Vanadium, yeah. There you go, vanadium, V. So this atomic mass, this weighted average, is determined based upon the relative abundance of each of the isotopes. Now, let's stop here because this information didn't just come full bloom out of somebody's head. We had to agree upon a standard of weight, standard of mass. I should use that term, standard of mass. Used to be, the standard of mass was oxygen. But oxygen's a gas, it's difficult to handle. Not that it's toxic, it's just gases don't work well when you're doing analytical work. It takes special instrumentation and special care. But the reason oxygen was used first was because most of the metals in the Earth's crust are combinations, they're oxides. All right. The ancient term that they used was called calx. They're calxes. But oxygen was eventually abandoned for something more stable. And carbon was chosen. Because you can get carbon from almost any source. It's easy to purify. And most labs that are interested in this type of work will have the equipment where they can isolate the carbon isotopes. So we picked carbon, right, 6 protons, and a mass number of 12. That isotope is given 12 point infinity atomic mass units. Right? So that isotope, that atom, has a mass of 12 atomic mass units. Everything else is compared to that, even the other isotopes of carbon. Right? So carbon-13 is not going to be exactly 13 atomic mass units in its mass. It's going to be a little bit different than that. Now, the mass number 13 does tell us that it has, in addition to 6 protons, it has 7 neutrons. Now that's true. Mass numbers are always whole numbers. But atomic masses for the isotopes are not. The only one that is 12 with infinite zeros is carbon. And everything else is compared to that. So if we see the relative abundance by mass of carbon-12 is 98.89, that's why its average is 12.01. It's mostly carbon-12. And it's easy to isolate from organic substances. So when let's see, do I have an animation on the calculations here? Yeah, I do. Okay. So there we have the carbon 12, of course, is 12 exactly. And it's 98.89%. And we have to use a decimal equivalent. We're going to do math with it. All right, percent doesn't work. But 98% of 12 atomic mass units is 0.9889 times 12. So the way you would set that up is you would say, right, we have 12 atomic mass units, and the fractional abundance is 0.9889. Times that gives you a number. And then the abundance of the next most common isotope is carbon 13. But it's not exactly 13. It's 0034 atomic mass units. But its abundance is very small. It's like 0.011, 1%. Now there are other isotopes, but they're even smaller in amount than this one. Carbon 14 doesn't, I mean, it's used in the calculation, but it's also radioactive. You heard of carbon 14 dating. They use carbon 14 to date once living substances because it has a definite decay rate. Right? And over time, if you know how much you started with and how much you end up with, you can calculate how long it's been in the ground, how long the living thing has been dead. Okay, so when you multiply this out, and then add them together, you get the weighted average of 12.01 to 2 decimal places. Now that's going to be as just fine for us. 2 decimal places is enough. You'll notice on any periodic table that some of them have 4, 5, 6, 7, 8 decimal places. Those values will change the next time the periodic table is updated, but they'll change about the 5th or the 6th or higher number of decimal places. The second decimal place will never change. So that's why we just stick to 2 decimals. We can use an old chart and get perfectly good results for teaching purposes. All right. So here's another example. An element consists of 62.6% of an isotope with a mass 186.956 and 37.4% of an isotope with mass 184.953. So what's the average atomic mass? Let's do this one. Need a calculator. So we have 186.956 atomic mass units. But its relative abundance is 62.6%, which in decimal terms is what? 0.6260. So what's its contribution to the average atomic mass? 186.9556 times 0.6260. So its contribution is this much. Atomic mass unit. And the other is 0.3740. $184,953. Okay, let's see what that contribution is. times 0.374. And this one contributes 69.1724 atomic mass units. So now all we have to do is add those two together. We get 186.207. So this is the average value, right? And X with a line over it means the mean, average. Okay, so we got that value. Now it's asking us for the element. Which element is it? We don't have the number of protons, but fortunately, the atomic weight is usually different for each one. Some of them are pretty close. Then you need a tiebreaker, but most of them are far enough apart. So if you just look for 186.207, let's see, which one comes close? RE. I didn't have you memorize that one. RE is rhenium. Okay. So there are two ways to find out what your element is. If you know the proton, easy. If you know the atomic weight or the atomic mass, you can do that one also. Okay. Those are isotopes. All right, now we're going to look at the periodic table. Now that we know what the atom is composed of and its rough structure, we're going to get down into the weeds. And for that, the periodic table is very useful. Why do we call it the periodic table? Why not the element table? Well, it goes back to, trying to think of his first name, Mendeleev. Mendeleev, who put the first periodic table together. What Mendeleev, he was Russian. That was before the communists came in. They were actually doing some useful stuff. Once the communists came in, the country just went to them like that. He organized his table according to groups, right? Elements that had similar chemical properties. So we get the halogens, they all very similar in their chemical reactivity. The alkali metals on the far left, lithium, sodium, potassium, rubidium, cesium, those all have similar characteristics. So he grouped them together. And he noticed that as he moved from left to right in his groups, he'd have a group here and a group here. It got down to the end, say it got down to argon. So you have argon down here. And then he had an element out here that had 19 protons, right? And it didn't need a separate group because it had similar characteristics to sodium, which was over here, 11, right? So he said, that one needs to go down here, and it turns out it's this one, potassium. So rather than just string it out like that, he said, I'm going to put this one over here because it's like sodium, behaves like sodium. What he did was he went through this sequence and wrapped around. That's a period. You know what periodic motion is? Has anybody had physics in here? Okay. Periodic motion is motion. An object is moving, but it doesn't go anywhere. It just goes to this position, and then it goes back to where it started. So periodic motion can be in like a circle or an ellipse, or it can be like a grandfather clock with a pendulum. It can go back here, back to where it started. That's a period. A period means one cycle of something. Right? A period of the Earth's movement around the sun is 1 year, 365.25 days. So that's where he gets the name period. It goes through one cycle, starts over again. All right. Oh, okay. So we're going to give credit to some other guys here. Johann Wolfgang Dobereiner. But you don't know what country he came from. He's German. He noticed in and published in 1829 his triads. He noticed that there were 3 elements, and we didn't know all the elements. At that time, we knew maybe roughly 60 elements. He noticed 3 element groups where they had similar characteristics. And he called them triads. That's as far as he took it. Then Julius Lothar Meyer, I think he was German too. He introduced the concept of valency. Actually, I don't think he was the only one. He popularized valency. And he created a table of the elements similar to Mendeleev's in 1870. But he didn't take it any further. He just slapped them in a table and said, that's it. Didn't try to use them for anything that I know of. Then Dmitri, there we go, that's his name, Dmitri Mendeleev. He put his periodic table about the same time as Meyer. The difference that Mendeleev introduced was that he noticed that groups of elements, and of all the elements that were known, if you just move from left to right and top to bottom through your periods and add them in there, so sometimes he tried to add one in that was in the wrong group. It didn't have the characteristics of that group. He says, wait a minute, this one has the characteristic of this group over here. So he stuck it over there and left a space. Okay, he says, there's going to be one of these days, somebody's going to find an element to fit that space. And it's going to have this mass, it's going to have these chemical and physical properties. And he named them and offered values, calculated them. And that's why Mendeleev gets the lion's share of the credit for the periodic table, because he used it to predict the existence of yet to be discovered elements. In fact, he predicted gallium and germanium. If you look over there, aluminum, Al. Underneath is gallium. To the right of it is germanium. There was another one, technetium, which is radioactive. It's under manganese. And there was another one that I left out there, scandium, Sc, right next to calcium. He predicted that one also. Oh, there we go. I didn't have to remember his name after all. So Henry Moseley was an Englishman. He was a pretty young fella. He's like in his 20s. And he was doing research as an undergraduate, actually, and then as a graduate in X-ray spectroscopy of the metal elements, which means he just took pure metals and he fired X-rays at them. And looked and recorded the spectra. At that time, you could record spectra on photographic plates. And what he noticed was that one particular line of the spectra, I'm not sure how he figured out which one to use, but he could determine the frequency for each of the elements, had a unique frequency. And in his formula, all he had to do to go from, say, potassium to calcium to scandium to titanium is just increment this number by a factor of one whole number. So you put that number in there, and just incremented it by 1. And each one would exactly calculate the frequency of light that was emitted by that element. Right? He didn't associate this number with the number of protons yet, but that's what he was doing. He was exciting the nucleus. The nucleus was emitting radiation, giving him a spectrum. And in his formula, so he actually discovered the atomic number. He didn't identify it with protons, but he would have, I think, if he had lived. But notice this is 1913. 1914, World War I broke out. And he was a patriotic Englishman. He joined up, went off to war, got killed. So that was the end of his scientific career. But at least he contributed that much before he left. All right. So we got this. Everybody got a copy of the extra credit periodic table? You're going to build it? Okay. So groups used to be called families. And periods are left to right, groups are vertical. Actually, Mendeleev's first chart was flipped 90 degrees. His groups were left to right and his periods were vertical. But the second publication, he rotated them. Now he had some periods go left to right. And that's where they've been ever since. Some of the groups have names. The first one on the left, and this 1A, 2A, these are old systems of numbering the groups. The new system, both the new and the old are in that periodic table. The number on the top of each group, 1 through 18, is the new system. The one below it, 1A, 2A, and then you go across the boron, say 3A, 4A, 5A, 6A, 7A. And I don't know why they don't say 8A, they just say 0. I think it should be 8. Anyway, those Roman numerals tell us how many valence electrons are in each atom. Now, I know that doesn't make any sense to you right now, but it's useful. Now, when you build the table that I gave you as extra credit, you use the new system, 1 through 18. But each one has, some of them have names. Like the first column on the left is alkali metals. The second column is alkaline earths. Then you move over to the far right side and you get the noble gases. Okay. To the left of them, the halogens. Right? Everybody knows these kind of orangish green lights in the parking lot at night coming from those lamps up there. Those are halogen-based lamps. I think they use chlorine. No, iodine. I think they use iodine in those lamps. So those are the halogens. Next to them are the oxygen group, or the chalcogens. CHACOGEN. The CH is a hard C, K, chalcogen. From the word calx. And then next to them are the pnictogens. Starts with a P and the P is silent. And then you have the central group in there that starts with scandium, ends with zinc. In that region, they're called the transition elements or the transition metals. And then down below, you have the lanthan. Actually, the proper term is lanthanoid, but you can call it lanthanides. That's the way we used to call it. The lanthanides start with lanthanum and work through cerium through lutetium. And then the actinides are just below them, actinium, thorium, through uranium down to lawrencium. So those are the ones that you'll identify on your table. Now, those two rows down below, we stick those right up there between barium and hafnium, or radium and rutherfordium. And they're pulled out for two reasons. One is keep the chart from being a mile wide. And the other is that the outer shell electrons, we're going to talk about later or very soon. The outer shell electrons are all the same positions around the atom for those groups down there. It'll make more sense in a few minutes. All right, when we look at the periodic table, we can name those groups, and there's one major division: the metals versus the non-metals. Metals have basic physical characteristics. Non-metals have different characteristics. So that solid black line that goes between boron and aluminum and then stair steps down one at a time. Don't stair step two. Right? We're taking these steps one at a time. We're not trying to get to the top in a hurry. So goes between boron, aluminum, and then aluminum and silicon, and then silicon and germanium, and then germanium and arsenic. And everything on the right is non-metals. Everything on the left is metals. Right? So what are characteristics of metals? Let's see, do I have a slide on that? Yeah, metals. When they're polished, they have a luster. Right? You can make mirrors out of them. In fact, in ancient times, mirrors were just polished metal. Now we make mirrors with glass, and then we coat the back of the glass with silver, chemical process. And then we cover that with something to keep it from getting scratched. But the metals, polished metals, have luster. They are very conductive thermally, right? They conduct heat very well. In fact, the most efficient heat conductor is which? Anybody build computers? No? Silver. So when you take your CPU and you put it in on your motherboard, you put a paste on top of it, not underneath, right? You don't want to put a paste on the contacts. Once you get it down, you put a silver paste on top of it. Then you put your heat sink on top, whether it's a fan or if you have a liquid system, it'll go to a heat sink of some kind. But you use that silver paste because it's the best conductor of heat. Electrical conductivity, right? Metals like to give up electrons. They love to shed their electrons, some of them more than others. And those electrons are free to move. So if you make that pure metal into a wire, you can conduct electricity a great distance without losing much voltage. So the ideal conductor is in most people's house, it's copper. Right? It has to be very pure, 99.999% copper in those wires. That's why people steal copper wire. Of course, sometimes we have to use something that's a little cheaper, right? So these high tension wires are made of aluminum, but they have a specific structure to them. We won't have time to go into it, but they all conduct electricity very well. They're malleable. That is, you can take a chunk of them and shape it, right? In fact, pure iron, you can scratch it with your fingernail. It's very soft. And it's not just malleable, but it's ductile. Ductile means you can stretch it into a long wire. All right. Non-metals. Oh, and all the metals except for one, except for one is solid at room temperature. Which one is liquid? Mercury, yeah, mercury. That's why we use mercury in thermometers. Well, we used to. Now the OSHA and the EPA police say we can't use them anymore. I got a few squirreled away though. You just have to be careful with them, right? You don't want a mercury spill. We don't stick mercury thermometers in patients' mouths anymore, or the other end. We use electronic. Right? I gave blood yesterday and they stuck that thing in my mouth. I had a plastic sheath on it, but it was a thermocouple. You just stick it in under the tongue, and we use electronic interpretation of the signal coming from that probe to determine my temperature. It was normal. So that's the rest of them are solid. But for nonmetals, you have the full range. You have solids, liquids, and gases for nonmetals. Yeah, they have the absence of properties of a metal. All right. Actually, nonmetals are poor electrical conductors. They hang on to their electrons very well. There are some exceptions. Certain allotropes of carbon, allotrope is just an element in a different form. Right? Allotropes of carbon are like diamond. That's carbon. Or graphite. That's carbon. Nanotubes, carbons, buckyballs. You've heard of buckyballs? They're advertising a nutritional supplement now. They call it C60. That's a buckyball, right? It's carbon linked together in this geodesic structure. Looks like it came from Disneyland, Disney World. Anyway, they're poor electrical conductors, most of them, except for these versions of carbon. Some of these versions of carbon are very conductive. They're good heat insulators, right? The best insulator for carbon is diamond, right? It doesn't transfer heat easily. In fact, that's how gemologists determine if you've got a real diamond in your ring. They take this device and they touch it to the diamond, and it registers how much heat is transferred from the device to the diamond. And if it's very high, they know it's not a diamond. If it's very low, then they have a scale, and it tells them this is a diamond. So a friend of my wife's wanted to send her a tanzanite, right? This pretty blue stone, comes out of East Africa. So she received it in the mail, and we took it to a jeweler to see if we could find a setting for it, because it was without a setting. And they said, wow, that is a beautiful blue diamond. But what? It's supposed to be a tanzanite. So they got their device, put it on there. It's a blue diamond. And it was a couple of carats. It was big. So he says, okay, we like that mounting. Can you put it in that mounting? And while you're at it, appraise it for us so we can get it on our insurance. So we contacted her friend and said, I think you sent us a diamond. I said, okay, my mistake. Could afford it. So she got to keep the blue diamond. They have no luster. Right? They're very dull. These are nonmetals. I've already said they could be any form, solid, liquid, or gas. If they're solid, they're very brittle. And they're not ductile. That is, you cannot stretch them without breaking. You cannot mold them. They're not malleable. Let's see. Okay. That's good enough for now. That's a major division. So most of the elements in the periodic table are metals. Very few of them are nonmetals. Now that's significant when we start to build compounds. The way they behave, their chemical behavior with one another depends on whether you're trying to combine a metal and a nonmetal or two nonmetals. And we'll get to that. Okay, so there's your division. There's also a subdivision along that black line. Some of those elements, under certain conditions, behave like metals, and sometimes they behave like nonmetals on both sides of the line. So silicon, and we call those metalloids. Silicon is the basis of the semiconductor industry, right? All your computer chips. I mean, you can make computer chips out of other elements, but we use silicon because it's easy to make it pure, and we're trying to keep the cost down. So we use silicon as the basis for our semiconductors, and it can be doped to behave as a positive or a negative electron donor or acceptor. Arsenic, germanium, antimony, tellurium, those are all close to that line, and they can behave as either metals or nonmetals depending on their environment. Those are metalloids. And the list varies depending on which author you talk to. Okay. I'm not going to spend a lot of time on those. All right, now we're going to get into the weeds with electronic structure. Your book calls it the electron shell. This is the principal quantum number. Now, what I'm doing here, I go back to that original slide. I skipped to Niels Bohr and Erwin Schrödinger. Niels Bohr offered a model for the atom that allowed us to calculate energies. In other words, if you have and in fact, it only works for hydrogen. If you have one proton in the nucleus, you have one electron out here, you have various energy levels. And if you add energy to that electron, it will jump from one energy level to the other. It won't, not in between. It has to be exactly the right amount of energy, which means the right wavelength of light, to promote the electron to one of these upper levels. And he had an equation that would work for hydrogen or any element that was hydrogen-like. Right, we won't go into that because this is an introductory course. But he was able to quantify the amount of energy that was provided to that electron to move from each level. And each level had a number. And these numbers will go into your equations. Now, if that electron happens to be up here already, it's excited and it goes back, then it's going to emit a photon of light. If that same photon of light hits this electron, it promotes it. So it works both directions. That was Bohr's contribution. Erwin Schrödinger proposed the quantum mechanical model of the atom. So Bohr introduced us to the quantum. In other words, the electron only moves in discrete units. It's not continuous, it's quantized. And then Schrödinger took that further and developed a system of equations that would allow us to apply this model to all the elements. And that was, let's see, I think we would say this is the planetary model of the atom, because it looked at the nucleus as the sun and the electrons as planets. Okay. Schrödinger gave us I need a new one. The quantum mechanical model. And that's what we're going to introduce next in these subsequent slides. All right. Let's see. Where to use this? In his equations, in Schrödinger's equations, he has 4 variable numbers. The first one is similar to Bohr's 1, 2, 3, 4. the principal quantum number. Is it LE? Yeah. That's right. AL is like the principal of your school is your pal, PAL. That's the principal. LE is the primary. Principal quantum number. Okay. This refers to the region of space where the electron is found, and all electrons in that region have similar energies based upon the Bohr model. And your book is going to call this a shell. Okay. The lower the number, the closer the electron is to the nucleus. Okay. So you can't get any closer than number 1. And the numbers that can be applied to this N are the whole numbers. 1, 2, 3, 4 on up. Okay. The subshells are given the letter L, and these are the angular momentum. Quantum number. Let's see, subshells. There's more to it than that. I want to see if I'm explaining it. These refer essentially to the shape of the orbit. So they could be spherical, they could be kind of dumbbell shaped, they could have donuts. We're not going to go into that much detail. But the numbers that can be applied to this one, think of it as a branching root or a tree. So if you start with one of these, then one of these can give rise to several of these. And each one can give rise. So for this one, you have the possibility of 0, 1, up to N minus 1. So let's just say, for example, we use a 3. We're at N equals 3, then we can have as many L's as 0, 1, and 2. So we can have 3 out of that one shell. We can have 3 subshells. Okay. All right. Oh, and when we start building electronic structure of an atom, using these numbers can get to be messy. So we assign letters to these subshells. So if we have a 0, it's an S. If we have a 1, it's a P. A 2 is a D. And say we went to 4, we'd have 3. And that would be an F. And actually, that's as high as we need to go for all the elements that we know now. You can go higher. So if we promote an electron from an F further up, then you can go to a G and so forth. The M sub L takes one of these. That's the angular momentum. This is the magnetic quantum number. It's based upon one of these. So let's say we have a 1, a P subshell. If we have a P subshell, then we can have negative P, we have -1, and we increment by units, -1 to 0 to +1. Okay. If we had a 2, we could go -2, -1, 0, +1, +2. If we were at a 3, we had possibilities of -3, -2, -1, 0, +1, +2, +3. Okay. Kind of balloons. Now that's going to make a whole lot of sense. I'm going to show you how it fits with the periodic table in just a minute. And then the last one is the easiest one. Let's see, I'm going to move it over here. M sub S equals the spin quantum number. Each electron is viewed as a spinning top. And it can either spin this way or this way. That's it. So the numbers that we give it, this one are +1/2 or -1/2. That's it. For any one of these, you can have you can have 2 of these in each one of those levels. So each one of these M sub L's can have 2 electrons only. That's all it will hold. Okay. So the number of, shell, subshell, this is called an orbital. There we go. So for each one of these orbitals, it can only hold 2 electrons. So if we have a P subshell, we can have 3 orbitals. And how many electrons? Maximum 6. 2 times 3. Those are some shapes, angular momentum, SPDF. S's are spherical, P's are dumbbell shaped, D's are double dumbbells. Actually, D's can have some donuts in there too. And then F, they get ridiculous. Now, these shapes are not observed. They're statistically predicted by the equations. Okay. We didn't get down, we don't have a microscope that can see them. But they quantify where the electrons are most likely to be found and their energies. So that way, we can make predictions about movements of electrons, reactions that may occur, those types of things. All right. So if we have a P or an L equal to 1, we could either have a -1, a 0, or a +1. -1 would be the dumbbells on the x-axis, the 0 would be on the y-axis, and the +1 would be on the z-axis. And each one of those can hold 2 electrons. Each one of those orbitals. Okay, I've talked about that already. There we go. So the space in which electrons move rapidly about a nucleus is divided into shells, subshells, and orbitals right there. All right, before we get into these rules, I want to point out how the periodic table is structured. Let me just draw or rough out a periodic table. So we have it like this, that, here, here, that. Then we have these, and okay. Think of building an atom, 1 proton and 1 electron at a time. And you start from the innermost energy level. Right? So hydrogen in its ground state would have one electron, and that electron would be in this principal quantum number, this subshell, and this orbital. Okay, so we would say 1s with one electron. So for hydrogen, we would have the electronic structure will be 1s with one electron. That's the way you'd write it. Now think of, as we move from left to right, as we're adding electrons, which subshells are being filled? Well, if we go from hydrogen, let's leave out hydrogen and helium because they're kind of special. Let's go down to lithium. Lithium, we're filling an s orbital. Well, now it's the second level. Now it's 2s. 2s1 is lithium. Well, actually, that's not the only one. I'm sorry. We've already filled 1s with 2. Now we have a 2s with 1. So we have 3 electrons to balance 3 protons. So you're filling the highest energy is the one you're filling, and you can see that in the periodic table. The first 2 columns, you're filling s orbitals. Right? This s orbital can only have a 0 for its, this s subshell can only have 1 orbital, and that can only have 2 electrons. So that's why you only have 2 columns there. 2 electrons and you're done. You're done with the s's. Then if you move across, you're still adding electrons. You get into the right-hand section. Now what are we into? We're into p's. Once you get to p's, now you have the possibility for how many electrons? 6. Look how many columns you have there. 1, 2, 3, 4, 5, 6. Moving from left to right. You're putting a new proton, a new electron in each one. You can have 6 of them. So that those 6 columns on the right, those groups, you're filling p orbitals. The first 2 columns you're filling s's. The last 6 you're filling p's. And then once you get to d's, 2, then you have the possibility -2, -1, 0, +1, +2. Right? 2 electrons each, you can have 10. 10 elements to fill up the last of your orbitals. And look how many there are. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. 10 elements. The transition elements, you're filling d orbitals. Okay? So you see where I'm going with this? If we go to F, where you have 3, you can have -3 and +3. So it's 1, 2, 3, 4, 5, 6, 7, 14. You can have 14 elements there to accommodate the electrons. Look at the lanthanides, cerium, PR, praseodymium, I think, neodymium, plutonium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, TM. Don't remember that one. Ytterbium, YB, and lutetium. There are 14 elements there. You're filling f orbitals. That's how the periodic table is constructed. Why it looks the way it does. Okay? Now, okay, so this is s orbitals. These are d's. These are P's and these are F's, regions. All right, now for the rules. The Aufbau rule says that as we build the next element, as we add a proton, add electron, these subshells are filled in increasing energy. They have to be closest, if there's a space close to the nucleus, you've got electrons around here already, say you're going to add another one. It has to go into the next highest energy level, right? You can't stick it way out here just arbitrarily. It has to go very next one. That's Aufbau. That's a German word. I'm not sure what it means. I like to say Aufbau means do it this way. Then you have Hund's rule. When you have orbitals, say we have, we're looking at p orbitals. So if we look at the p's, we can have 3, right? -1, 0, +1 orbitals in that subshell. Okay? When you start filling in electrons, say we want to use this one for 1 electron. And that's what I call spin up, or +1/2. And say you need another one, right? You add another electron. You add another electron. You got to put at least 1 in each one of those orbitals before you can go back and pair them up, right? So this is +1/2. That would be -1/2. And then you go to the next element. You need another electron. That's where they go. That's Hund's rule. You have to spread them out, right? It just makes sense, right? Electrons are negatively charged. You want to keep them separated from each other until you have to put them together because they're repulsive of being the same charge. And then the Pauli exclusion principle. It simply says that no 2 electrons can have the same set of 4 quantum numbers. Those 4 quantum numbers are unique for every electron in the atom. All right. So if we have to follow the Aufbau principle and fill these orbitals, increasing energy, as we get more and more protons and electrons in the atom, they tend to shift the energy levels such that sometimes a 4p might be lower energy. Let's see, a 4d might be more energy than a 5s. Right? We look there toward the top. So when you get to that level, then things start to shift based upon the quantum mechanical equations, actually. Right? All these calculations have been done for us. We don't have to do that. So how do you know when you're filling these, putting in electrons from the next element, the next element, the next element, how do you know what order they go in? Right? There's a real slick way to do that. Actually, there are 2 ways to do it. I'm going to show you the longhand way and then the shorthand way. Let's see. I'll leave that up there and just use this part of the board over here. Because if this stuff is, well, of course it's new to you. And it's probably got you cross-eyed already. This energy order is the easiest way to do it, longhand way, is think about, well, first of all, if we have a principal number 1, how many subshells can it have? Well, 1, you have to start with 0, and you go up to n-1. So n-1 is 0. 0 is all you can have. That's it. You can have 1s. That's it. Right? Then you can go to 2. Well, let's do it this way. Then you can go to 2. How many can it have? Well, with 2, you can have 0 and 1. Right? N minus 1. 2 minus 1 is 1. So you can have a 2s and you can have a 2p. Right? If you go to 3, you can have an s, a p, and a d. Right? Because 3 gives you a 0, 1, and a 2. You can have 3 of them. S, P, and D. If you go to 4, then you can have an S, a P, a D, and an F. And if we go to 5, you can have an S, a P, a D, a F. And I could put a G out there, but we don't need it. Because we're only filling F as our, that's the highest we can go. So let's see, our example there goes to 6 and 7. So we can have S, 6, 7, 6, 7. Let's see, I don't think I need that 7 down there. This is a P, this is a D, and this is a P. Okay, so when you're filling, when you're building atom, next element, next element, next element, you can go that way, that way, that way. That means you do 1s first, then 2s, then 2p, then 3s, then 3p, 4s, then you go back to 3d. You go to 4s before you go to 3d. Then you go down that like that. This diagonal tells you where you go next. Okay? So if we draw out, if we put these out in a string, then you would go 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p, 5s, and then you would go to 4d, and then 5p, 6s, back up here to 4f, and 5d, 6p, 7s. I guess we need to keep going, don't we? 5f, 6d, and 7p. So you don't go 1, 2, 3, all 3s, and then all 4s, and then all 5s. Based on the quantum mechanical equations that solve these problems. So if we filled all of this one up, right? S's can only have 2 electrons. 2, 2. How many can P's have? 3 times 2 is 6. Then we got 2 again, then 6, then 2. The D's can have 10. This is maximum, right? So we keep filling, and we get to this point, and now we only have maybe 3 electrons, and that's where we would stop. So what element is this if it's neutral? Right? 2, 4, 10. 2, 4, 10 is 20, 30, 33. 33 electrons, which means 33 protons. That would be arsenic. Okay, that would be the electronic structure of arsenic up to there. Notice that the periods correspond to the principal quantum number n. So the top one is N1. The second one starting with lithium is N2. 3, 4 is potassium, 5 is rubidium, 6 is cesium. Okay? So that works for the S's and the P's. So if we go across from sodium, magnesium, aluminum, we go from those 3 S's to the 3 P's. There we go. And then we finish with these, we swing around to the 4 S's, potassium and calcium. But then we get into the D section. The D's can only start with 3s, right? 2s can only have S and P's. So the D's pick up with 3. So once you get to the 4, the period 4, and you start with scandium, you have to back down to 3D. That's why this one's here. And then you can fill it up, and then you can go back to 4Ps with gallium, germanium, arsenic, to krypton. And then when you get down to 5, right, we finished filling these up, 5S, rubidium and strontium. Then you go to yttrium, and it's 4D, right? You back up 1 for the Ds. Okay? And you go across with those, fill those up, and you go back to 5Ps with indium, tin, antimony. Then you swing around to 6S, and you get cesium and barium. Then you get lanthanum. We're going back to 4Fs. Okay? So when you get down to the F, the lanthanides, you have to back down two spaces because you need 4 to get Fs out of it, right? 0, 1, 2, 3, S, P, D, F. Now, this chart gives you, okay, lanthanum is going to go to 5D. Lanthanum is 5D. 6S, 5D. Then you get into the Fs. Right. I'm not going to have you do the Fs. They get really, there are some anomalies in there. Actually, there's some anomalies in the scandium through zinc level. We may talk about those. I just want you to be familiar with this, and we'll do. Oh, I forgot I put that in there. It's diagonally, not diagonally. Okay, this is known as the electron configuration. So if we take examples, I'll leave that one up there since we've already extracted it from our diagonally. Keep that there. If we do nitrogen, okay, nitrogen has how many protons? 7. So the neutral atom will have 7 electrons, right? So if we say 1s2, 2s2, we've already used up 4 of them. So now we're into 2p's, right? 2p's, what do we got left? 3. 2p3. That's the electronic configuration of nitrogen, neutral nitrogen. This is known as condensed notation. Let's see. Sometimes the orbital diagram helps. Now, the preparers of the slides, the authors of the textbook, prepare these slides for instructors. I don't like to use boxes. It's too busy. I mean, it takes too much effort. So if you're going to do, what I do is just draw a line here. P's can have 3 in them. Right? -1, 0, +1. This would be up, down. Up, down. This would be 1, 2, 3. All 3 are up. Or +1/2. Okay. To obey Hund's rule, we got to fill these up first before we can go further. Okay. How about sulfur? Let's see, let's find sulfur. Right under oxygen, 16. Okay. So this could have 1s2, 2s2, 2p6. That's 10. We got 6 more. Where do we go from here? 3s, 3s2. And then 3p what? Let's see, that's 10, 12. We got 4 more. Okay. So if we showed where the electrons are in each one of these levels, these 2 here like that, those 2, these 6 like that, all paired up, these 2 paired, then we have 4 here, up, 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 and down. So that's what that would look like for sulfur. Okay. These can get really complicated when you get to the bigger atoms, like barium. How many electrons does barium have? 56. Okay. If we did barium, we'd have to go out here and then swing around and put some more underneath. So here's what we do. We use an abbreviated condensed version. Look where barium is. It's in the 6th period. If you back up to cesium and then back up to the next period, we'll go down to xenon. Characteristic of the noble gases. All of the shells, all of the orbitals in noble gases are completely filled. They're full. So if we say, let's start with xenon at 54, what's left after xenon? 6s. 2. Right? So we use this as our core, and this is what's beyond the core. So xenon is going to be, let's see, up through 5p, up through here. All those are completely filled with electrons for xenon. And then we get to 6s for barium. And that shortens things, makes it a lot easier. Because in chemical reactions, we're really only interested in these electrons out here, valence electrons. The highest principal quantum number tells you how many valence electrons you have. So 3 tells you 1, 2, 3, 4, 5, 6. Sulfur has 6 valence electrons. Those are available for reaction. These are not. Those are core electrons. So barium has only 2 valence electrons. And strontium only has 2. Calcium only has 2. Magnesium only has 2. Beryllium only has 2 in their outermost orbitals. That's why they behave alike. Because they have the same number of valence electrons in their outer shell. For the alkali metals, they only have 1. They're like 2s1. Sodium is 3s1, 4s1, 5s1 for rubidium. Cesium is 6s1. That's it. That's all they have. They just have that 1 electron. That's why they behave alike. Okay, so barium should be, well, there it is, and then the abbreviated form. Okay. So the electronic configuration of sodium, let's see, where's sodium? There it is, 11. Sodium has 11. Right? Well, let's see. Sodium is going to have 1s, 2s, 2p, all filled. And that gives us 1 left over with a 3s. So which one fits that one? 1s, 2s, 2p, B. Looks like B is the right one. Yep. It just takes practice. Right, I already said that. The electronic arrangement in the outermost shell is the same for elements in the same group. That's why they have similar properties. So in the 1A group, that's where we get that old style. The 1A, 2A, 3A, those Roman numerals tell you how many electrons are in the outermost shell. Now that works pretty well for the alkaline metals, alkaline earths, and all of the other elements to the right, the p orbitals. The s and the p orbitals, it works great. When you get down into the transition metals and really bad in the lanthanides and actinides, then the water gets really murky. But for the representative elements, they call them, the first two columns and the last six, those are representative elements. It works really well. And let's see, has anybody had biology or anatomy and physiology? Okay. Yeah, they mentioned the octet rule. That's the octet rule. The octet says two electrons in the first, 6 in the last makes 8. So if you have them all filled, the octet, you're going to have a noble gas, neon, argon, krypton, so forth. And that's what the other elements are tending towards when they react. They're trying to reach the octet. At least that's the simplified version. All right. So the valence electrons are the electrons that have the same principal quantum number. 1, 2, 3, 4, 5, 6, 7. Oh, there you go. Left out the lanthanides and actinides. They're the F areas. The distinguishing electron, I don't dwell on this too much. The last electron added to the electron configuration of an element, it just causes that one to be different than the one before it and the one beyond it. It's nothing, there's no magic. Okay. So how do we classify elements? We've done part of that already. Metals and non-metals. And then the others we described as, well, the representative elements of alkaline metals, alkaline earths, boron, carbon group, pnictogens, chalcogens, halogens, and noble gases. Now they're making a distinction between transition elements and intertransition elements. The transition elements are the ones that are filling the d orbitals in that middle group. The intertransition elements are the lanthanides and actinides because they're inside the transition group. There we go. Trying to make sense of it. Okay, elements in groups 1 and 2 fill the s orbitals. Oh, we're almost done, aren't we? When we get to concept questions, I think those are the last slides. So consider 2 elements. Let's see how we're doing on time. Coming up on 11. Oh, that's good. That's the end of lecture time. And we can take a break before lab. One element is a gas and the other is a solid. Okay. So we know that the gas is going to be a non-metal. And the solid could be a metal or a non-metal, either one. Each contain identical number of electrons in their outer shells. Oh, that means they're in the same group, doesn't it? Yeah, if they have the same number of electrons in their outer shells, then they're in the same group. So that means we're looking at a group on the right where we can move vertically from nonmetals to metals. It's like if we went from carbon, that would be a nonmetal, down to tin, be a metal. But they have the same number of electrons in their outer shell. Okay. These elements are metal and not, oh, I see. We look at our choices. Okay. Fluorine and iodine. That could work. Right? They have the same number of electrons in their outermost shell, but iodine's not a, let's see, one is a gas and the other's a solid. That would work. Fluorine's a gas and iodine's a solid. Number contains how many neutrons? All right. Does fluorine have 10 neutrons? Let's see. Well, the most common isotope of fluorine is probably 19. Yeah. The most common isotope of fluorine would be this. Right? Because its atomic weight is really close to 19. I mean, most of the isotopes are probably 19s, and you have some that are less. That's possible. How about iodine? Does it have 74 neutrons? Let's see. It's iodine is 53, and its most common is probably 127. 53 and 127. All right, so that'd be 74. It works for me. Yep, we found it. When you have a multiple choice question, work your way down. Once you find the answer, you can stop. Just move to the next one. All right, how about concept question 2? You're asked to determine the composition of a gas. There are 3 components with 3 different applications. They all have the same atomic number, but the number of neutrons is 0. Oh, 0, 1, and 2, excuse me. Yeah, finish reading. If they have the same atomic number and there's 0 neutrons, that has to be hydrogen. That's the only one that works, right? Right, you have 3 isotopes of hydrogen. This is 1 because there are no neutrons. This is 2 with 1 neutron. And this is 3 with 2 neutrons. This is deuterium, that's tritium. And I think this is called protium. Yeah. One of the components is used as a radioactive tracer in biological experimentation. Yeah, I think it's tritium. Identify the gas you're given. Here are the 3 components referred. Yeah, it would be hydrogen. Excuse me. There we go. Yep. The clue for me is no neutrons. That has to be hydrogen. All right. I think that's it. Yep.